Just a second, yes. Just a second, yet I have to change something with that. Okay. Okay, can you hear me?
Yes.
Oh, thank you. I have had some problems with the hardware, but now it's okay. Okay, let's start. Today's lecture of discrete mathematics will be focused on division, on calculating the divisors or the rest from the division of some number by another, and about some algorithms connected to them. We are slowly going to discussion about algorithms connected with discrete mathematics, so such a direction which goes to computer science slowly. Discrete math, lecture 3. Division algorithm. Okay, so let's assume that we have two numbers, m and n, and we would like to divide one by another. Let m such a line n, sorry, maybe means m divides n. Okay, so if it is, let it be 6 divided by 3, it's no problem. But if we have 7 divided by 3, and we are talking about calculation in integer or natural world, there is a small problem, yes, because we have something like the rest, or the question in general: is it possible to divide 7 by 3 in this world of discrete values? Okay, so let it define. M divides n means that m is different than 0, and n is m times k. This k for some value of k, and all of these numbers n, m, and k are integer ones. Integers. So this is quite natural, but in such a case, there is a question, because 3 doesn't divide 7. Yes, this is not true. Okay, so we'll have a kind of special numbers we will call dividers. And in general, it goes to quite big mathematics. For instance, if we have 15, this is 3 times 4, 5, and 21, this is 3 times 7, and so on. And every number, as you possibly know, it can be factorized. That means written as a multiplication of so-called prime numbers. And this distribution, this method of finding these prime numbers is quite difficult. This is the base of very strong cryptography course, RCA. Maybe this is for another lecture, but we have such a fact that numbers can be divided by another number. We have divisors, of course. If we have only, for instance, if we have 7, so the divisors of 7 is only 1 and 7. Yes. And another can be multiplied by another prime number. Okay, but let us go further here. If we have this 7, we can divide with the rest. So it is some kind of method to not leave the word of integer numbers. Let us write it like this. Suppose n and m integers, n greater than m. Of course, this it doesn't matter, but this is better for thinking that we divide n by m. When we divide n by m, we obtain following equality. N equals m times something, let it be q, plus r, where r is between 0 and m. Of course, this is strongly lower than m, because if it is equal, we have r0, and it is like this is like this situation. So this r will be called the rest. And we are interested how to compute this q and this r. We are interested in how we can compute q and r. We can write it like here. If n is n times q plus r, we can write that we have divided by m. We have n divided by m is q plus 1 by m. That means that is we can write that q is a floor of n divided by m, and this is something we can call, of course, this integer part of this divisor, but it is quite easy to compute it. Some example, let it be this 7 divided by 3. If we write 7 divided by 3 and take the floor of this, so this is 2 point something, yes. Yeah. Oh, like this. So this is 2, and we have 2 times 3 will be 6, and this will be the nearest value where we are close to 7. With the rest will be 1. This will be q. R will be n minus m times q. So this will be 7 minus 6. This is 1. Okay, and let us consider the following operators. Consider following modulo and div operators. They are quite intuitional, even on some calculators. We can find such a patterns. So the modulo, this will be and modulo m will be the rest after dividing n by m. And of course, here this is this r, yeah. And div integer part, integer quotient after integer part of the factor n by m. So this is this q. As some examples, this is quite natural, but it goes to very interesting algebras, especially connected with modulo operators. It is a special kind of groups which are calling modulo groups, and they are quite unintuitional in some sense, but very useful. Example 1. So 7 modulo 3 will be 1. This is the rest. 1 modulo 7 is 1, because this is the rest from dividing from 1 by 7. If we divide 1 by 7 in integer numbers, q is 0, yes, because this is 0 times to place 7 inside. Because intuition is quite nice. If we have a number n, yes, we put here this m a number of times. This number of times we call q, and here we have the rest r. So if we have n equals to 1 divided by 7, so 0 times we can put here 7. This is just the rest, just the result of this r. 7 divided by 3 is 2. 1 divided by 7 is 0. 7 divided by 7 is 1. Also, we can try to use negative numbers, and this is also quite intuitional. Maybe let us look at on the figure. That's the line 0, and if we divide, let it be 15 by 7, so we have 7, and the rest 1. Yes, so 15 modulo 7 is 1. If we take minus 15, so the result will be like this. Here we can put 7, and this will be 6. Like here, just here. So the modulo operation can convert negative numbers to the interval from 0 to n minus 1 modulo group. This is group in formal sense. That means from mathematical point of view, this is a set with the operator. Operator is adding. We have neutral element as 0 here. So this is normal object from mathematicians. From our point of view, this is quite interesting operation, because in the computer inside, in fact, we are calculating in modulo algebra, because if we have a number of bits, for example 16 for a number, and if we are exceeded, we go to the negative numbers, because in fact we still in this 16 bits representation. So this is quite normal for computer scientists to feel by modulo algebra. Yeah. -3 modulo 7 would be 4, etc. Modulo in C language, for example, modulo in C or C++, it's written like a percent. So we write it like -3% 7. Yeah, so this will be 4. Okay, is it clear? It should be quite understandable. Yeah. Thank you. Okay, so if we know such a notation. I have
a question.
Yeah.
Are we going to describe the Euclidean GCD algorithm?
Yes, we'll go to it.
Okay.
But this is just an introduction. In fact, the Euclidean algorithm or determining of the greatest common divisor is close to another task, which is much more difficult. Maybe let us write it as a task for us today. There is something called Diophantine equations. Diophantine equations. Something like this. Let us write maybe Sx 7x plus 15y equals to 3. Yeah? And it is quite easy in the real numbers world, but the question is, if we assume that x and y are integers, if we can know the solution. This is quite difficult, but the Euclidean algorithm and this, in fact, reverse Euclidean algorithm, and these things connected with dividing numbers is the method for showing how to try to solve this. This is quite difficult because in the normal world, we just put the one variable in one side, another to another side, divide by 15, and we have the result. Yes, but in integers, this is not so easy, and even dividing by in such a discrete sense is not a proper way to solve this. So how to solve this equation? This is the question for today's lecture. The answer will be maybe not so easy. Sometimes we can solve it and sometimes not. Of course, one can guess the result, and this is like calculating the integrals. The best method for find the integral is just to guess the result. Yes. I have had such a colleague in the high school. If we have an integral, yes, like something, yeah, to x squared minus 5 dx, and how to find this function, yeah. So the best method is just guess the result, calculate the check if it works, and just put the result. Of course, we have many methods of calculating integrals. but there are no general one, and some integrals are impossible to calculate, like this e to x squared. There is no classical function we can put here, but this is another topic. But guessing the result is a method of mathematicians to solve some problems. And here maybe this will be the easiest one. However, sometimes like here I don't see the result. Okay, this will be our goal. But let us define the greatest common divisor as a base of some operations. Closing us to this question. The greatest common divisor, GCD, of two numbers. So let us define it like this. Maybe on an example. Firstly, we have 15 and 21. Yeah? So we are looking for the number such that this divides both these numbers, and this is maximal one. So here, because of 15, this is 5 times 3, and 21 is 7 times 3. So this is probably 3 here. But from the definition, the greatest common divisor of two numbers m and n would be such a maximal from such a numbers k, that this k is greater than 0, and k divides m, and k divides n. Of course, without the rest. Such a notation means that just this is the divisor. So this divides both. That's clear. Yes. Of course, the method can be just find the factorization of the number. Yes, this is 3 times 5, and this is 3 times 7, and just take the factors, which are maximal one. But factorization is in general a very hard problem. If we have such a small numbers, we can make a kind of brute force inside our brains and write it. But if we have, I don't know, 1001, who knows what is the factorization of this number? Maybe this is prime number. Possibly yes. I don't know. In general, this is very hard mathematical problem. How to factorize this, write the factors of the numbers, which means this prime numbers, which we can multiply of obtaining the number. So in general, this is not the way, and we have something called Euclidean algorithm, which is quite nice. Its computational complexity is maybe not so easy to calculate, but in general, it works quite fast. Maybe let us write it in words. So the greatest common divisor, the greatest common divisor of two numbers, m and n, is the largest number that divides, of course, without rest, m and n. Of course, we can use this number to compute the fraction if we divide one number by another, where they are relatively prime. Relatively prime would mean that no common divisors except one. So this is quite quite useful, but let us try to show how we can obtain it. Okay. Let us assume that n is greater or equal to m, and let us divide. Let us divide n by m, obtaining n equals to m times q plus r, where m is between, r is between 0 and m. This leads to following conclusions. First, if r is 0, so we have dividing without rest, then greatest common divisor of m and n should be m, because m just divides n. So this is the greatest number which is which can divide n, and of course divides m. It shouldn't be greater than m. This m. Yeah. So this is the smaller of these numbers of their common divisors. If the rest is not 0, then we can write that r is n minus mq, like here. Hence, it follows that every number that divides n and m and m also should divide r, because if something divides this right side, should also divide the left side. Divide n and m also maybe divides r. Therefore, the greatest common divisor of n and m also divides the rest. And this observation is the base of something we call Euclidean algorithm. That means the way to compute the value of this operator. Okay, an example. If we have the greatest example, example 2, greatest common divisor of, let it be, 48 and 46. This will be, if we find such a number, this is 2 times 23, yes. 23 is prime number, and this is 2 times 24. So probably this will be the greatest common divisor of, if we divide one by another, we'll obtain the rest 2. Yeah, so 48 is 1 times 46 plus 2. So this is greatest common divisor of 2 and 46, and this will be 2. Yeah. So this is just such a, we can write even that 48 is 1 times 46 plus 2, and 46, taking this and this, is 2 times 23 plus 0. Yeah. So, in fact, this is a part of the algorithm, but this observation is the formal base of taking under consideration smaller and smaller numbers. Even if we have very big numbers, after a few steps, in fact, this number of steps is behaves as a logarithm. That means in logarithmic number of steps, we can obtain the greatest common divisor. However, this is not easy to show the real computational complexity. Somehow, I remember that computational complexity of Euclidean algorithm is somehow connected with logarithm, but not for all cases, and we can think about it that this is quite fast, but not without formal showing the complexity. Okay, so let us try to write the Euclidean algorithm, and next go to the Diophantine equation. I will change the color. I like to change the color because if I write the same whole time, this is boring. Euclidean algorithm. Euclidean Euclidean algorithm. Finding greatest common divisor of two numbers. So this algorithm concurrently compute, if the algorithm can compute, this is somehow human property, compute greatest common divisor on M and N, and find the solution of an equation M times X plus N times Y equals to K, where K is the greatest common divisor of M and N. So this is somehow connected with this, but in fact we'll obtain the solution only if we have here the greatest common divisor of these two numbers. So if we have 7 and 15 here, we probably can solve by this algorithm such a case in which we have here 1, because the greatest common divisor of 7 and 15, this is prime numbers, is 1. So we can compute it in such a way. But in another, probably also, because look, if we have the solution of such a case in which we have here 1 except of 3, we can multiply the whole equation by 3. Yes, obtaining here 3 and here 3y and 3x. So probably somehow we can go to this. And in fact, being following in this topic, this is the only case in which we can solve a Diophantine equation. One case there are two cases, but in fact there are one of them. We can solve this equation if and only if we have a multiplication of the greatest common divisor here of these two numbers. And in other cases, there is no solutions. So this is quite a strong result. And it was difficult in ancient Greek because it goes from ancient Greek, the Diophantes, this is a mathematician also, because of ancient Greek, 3,000 years ago almost. So up to now, there are no better ways to write something about it. Okay, so we write the following the steps of the Euclidean algorithm in such a way. What time is it? 52, okay. Okay. We write down the steps of Euclidean algorithm. Euclidean algorithm in such a form. We start from n and m, and we write something like this: that a0, this is n, is q1 times a1, a1 this is m, plus a2. A1, this is q2 times a2 plus a3, and so on, up to al minus 1 is ql al plus al plus 1. And we stop if this is 0. When we have here 0, we stop the algorithm. And al, so the previous one here in the previous line, this is this la, this is the greatest common divisor of n and m. So this is quite easy. Let's look for an example. Example 3. 20. Let us find the greatest common divisor of 12 and 21. So we write 21 is 1 times 12 plus what, 9. 12 is 1 times 9 plus 3. 9 is 3 times 3 plus 0. So we have here that 3 is the greatest common divisor of 12 and 21 is 3. Of course, this is symmetrical. It doesn't matter if we write here 12 and 21 or 21 and 12. And this is quite easy. Everybody should learn, in fact, in primary school this algorithm. But more interesting for us will be checking how to write the solution of this equation in such a case. Let us try. What time is it? 26. Maybe let us try to write it after a short break. Have you any questions to this part of the lecture? Question, remarks?
No, sir. No.
Okay, so we have 15 minutes break, and after the break, we'll show so-called reverse Euclidean algorithm. That means such a trick way to find this x and y. If we put here a numbers, and here we have greatest common divisor of the number, we can reverse this algorithm to obtain these values and solve the Ophantic equation for some cases. Okay, so this is it. This is the way. How, as Mandalorian said, 15 minutes break. Dobra. Okay, we'll continue. Just a second. Okay, I'm back. Well, with the greatest common divisor algorithm, and now we'll try to show how to reverse it to obtain the solution of the Diophantine equation by using these factors of the steps of the Euclidean algorithm. Okay. So now we are looking for the solution of the equation n times x plus n times y equals to greatest common divisor of m and n. M and n are constant. This is just input numbers. X and y are variables. We are looking for them. M, n, x, y are integers. M, n constant input in sense of computer science. X and y are variables. Variables we are looking for. Okay. So to do this, we determine two sequences of numbers. For this purpose, we determine two sequences numbers. X0, x1 up to xl, and y0, y1, yl, fulfilling such an equation: AI, artificial intelligence, equals to n times xi plus n yi for I equals to 1, 2, up to from 0 up to L. Therefore, for the last one, for I equals to L, we obtain AL. This will be the last one. This one equals to greatest common divisor of m and n, and this will be m times xl plus n times y. Maybe I will show it on the example, because on such a abstract values it looks quite strange, but for the numbers it will be much easier. Let us take this example. This is quite okay. Look here. Let us imagine that we have such an equation. 12 times x plus 21 times y equals to 3. Like here, we have n. It doesn't matter. This is, can be n or m. Maybe this will be n, and this will be m. Okay, let us write it in such a way. So it doesn't matter, but let the n will be greater than m. This is m, this is n, and this is greatest common divisor of 21 and 12. Okay, so how to determine these numbers? Firstly, we write this 3 as 12 minus 1 times 9. Yes, from this. Now we can write 9, this one, as 21 minus 12. And now we have, of course, there can be several steps on such a procedure, but lastly, we'll have only this n and m as here, here, and here, and n, and some factors of multiplications of them with plus or minus, but it doesn't matter, it can be negative. So now making the order, we'll obtain such a like this. Here we have 12, and here we have minus and minus, so this is plus. So in fact, this is 21 times minus 1 from here, plus 12 times 2. And you can check that this is minus 21 plus 24. And in fact, we have here our x and our y. So the solution is x equals to minus 1, 1 equals to 2. And this is the solution of this equation in integer numbers. Yes. So such a trick to make the reverse thinking of this sequence of steps make us possible to obtain the values of this multiplier. And in fact, this is the only way, because we don't know other solutions. This is interesting, but in fact, there are no other solutions of such a Diophantine equation. This is also not intuitional. Maybe there can be a pair of or something. Okay, how to write it in formal way? Continuing this in black part. X I and yi we determine in a following way. From two from this one, from this place, where does this? Just a second. X 0, y 0. Write it down. X1, X0. This is 0. Okay. By y, this is 1. Yes. Okay. Okay. Maybe in such a way. If we have such a notation that the next one we take on this consideration this construction. In fact, this is each step of the algorithm. We can write in such a way that ai plus 1 is m times x times I minus y plus n y I minus 1 minus q times m m x I plus n y I. And this will be exactly m times x minus 1 minus x I q plus n y minus 1 minus q y I. So in fact, this is in shorter form writing that we use in a step. For instance, this part to writing how it can be written if we write this rest as the previous one, left, right, minus this part. Yes? For instance, here we have that 9 is 21 minus 1 times 12. And this 3, for instance, can be written as 12 minus 1 times 9, and so on. Yeah? So maybe I will make a little bit greater example to show it. Of course, we need an initial condition, but an initial condition we take just directly from obtaining the greatest common divisor. So because this will be on the right side. I remember that here we should have the greatest common divisor or k times the greatest common divisor. Because other possibility, maybe I will use a little bit wider whiteboard. The another situation can be like this, that we have here m times x plus n times y, but here we have equals to k times greatest common divisor of the m and n. This is also a possibility. Because in such a situation, in fact, we will obtain such equation in which we will use this x and y as multiplied by k. Maybe I will show it on an example. But firstly, let us make a little bit greater one as an maybe even as a theorem. Yeah, okay, that would be as a theorem about Diophantine equations. Have you any question to this part? This is in fact just a description of the algorithm. So maybe let us try to show the application. Example, which one? Fourth one. Using the Euclidean algorithm, find integers n and y satisfying the equality 333 times x plus 1234 times y equals to 1. Okay, next we'll put here another number here, but firstly let us try like this. So performing the Euclidean algorithm, we have something like this: 100,033. This is 3 times 333 because this is 999 plus 235. Okay, so we can write from this that 1234 minus 3 times this gives us this rest, 235. Okay. Next, we'll write this as we divide it with the rest with this previous rest. So this will be 1 times 235 plus the rest. The rest will be 98. And also here we can write that 333 minus 1 times 235 is 98. Next, 235. We'll write it as 2 times 98, and the rest will be 39. And also here we can write that 235 minus 2 times 98 is 39. This, the right side here is useful for writing back what is the solution of the Euclidean algorithm. This one, this is our goal. 98 can be written as 2 times 39. This will be almost 80 without 2 and plus 1920 probably. Yeah, and here 98 minus 2 times 39 is 20. And we have one step only now. One step, maybe 2 steps. 39 is 1 times 20 plus 19. And from here we have 39 minus 1 times 20 is 19. And 20 is 1 times 19 plus 1. And here, this is in fact the last step, because the next one gives us the rest 0. 1 times 19, this is 1. And here we have 19 is 19 times 1 plus 0. So this is the greatest common divisor. And now we go back to obtaining from this one something in which we have only these 2 constants and some multiplicators which we call variables. Okay, might be here. Let us use another color. Now we go back. So 1 from here is 20 minus 1 times 19. 20 minus 1 times 19. 19 here is 39 minus 1 times 20. Okay, so this is 20 minus 1 times, and we write what is 19. 39 minus 1 times 20. Let us make an order here. So we have 39 with minus 1, 39, and 20, and this is plus, so this is 2 times 20. Okay, now 20. 20 is 98 minus 2 times 39. So this is minus 1 times 39 plus 2 times and 20. 98 minus 2 times 39. Also, let us make an order. Here is 39 with minus. This is 2 and minus 2. This is minus 4. So finally, this is minus 5. Minus 5 times 13. Check me, because I am doing it online. A vista, a cappella. 39, and here will be 2 times 98. Okay, let us make here 39 notation. 39 is 235 minus 2 times 98. Okay, so we have minus 5 times this 39 from here, 235 minus 2 times 98, and plus 2 times 98. After making order, we have minus 5 times 235, and here we have minus 5 and minus 2, this is plus 10, and plus 2, this is 12. 12 times 98. Is it okay? Maybe. We'll check on the big. Maybe I even have some notations. Just a second. Minus 5 and 2. Okay. Up to now, it looks okay. Now 98. So we have minus 5 times 235 plus 12. Interact this 98 from here. This is almost the last step. 333. This will be the last constant we need. Minus 1 times 235. Also, let us make an order. So this is minus 5, and this is minus 12. So finally, we have minus 17 times 235 plus, and here is 12 times 333. And the last step, we should write this 235. Where is it? Here. As the 1000 something something minus 3 times 333. Okay, so we have minus 17 times this one. 1, 2, 3, 4 minus 300. 3 times 333 plus 12 times 333. So finally, we have something like this: minus 17 times 1, 2, 3, 4 plus, and here we'll have 3 times 17. What is 3 times 17? This is the question. 3 times 17 without calculator.
51.
51, sir.
Yes, exactly. 51. Thank you for your attention. 51 times 333. Just a second. Just a second. Is it okay? 17 minus. It looks okay. Let us check. Maybe with the calculator, because this is a strong mathematics calculator. So 17 times 1, 2, 3, 4. This is something like this. Whoa. Okay, with the minus, of course. 2000. 20,000 plus 97. Right. Okay, and now 51 times 333. Ooh, no, something is bad. Just a second. We should have some error somewhere here. But where? Because of course the result should be 1. So something is bad. But what is not good here? Yeah, sorry. Plus 12. 51 plus 12. So we have 33 finally here. 33, because this is 17 times 3, 51 with the plus 12 is 33. Okay, so this is 20,978 with the minus, and now 33 times 333. What is this? 63 times 333. Oh, this is best. So 20,000 979. Oh. Okay, so finally, as you can see, this is 1. So we have this x, this is x, and this is y, fulfilling the equation we would like to solve. Now, let us imagine that our equation is a little bit more complicated, but only a little bit. By such a way, in such a way, we have the same left side, but here we have, let it be 7. Okay. Of course, this 7 is a constant times the greatest common divisor of 3, 3, 3 and 1, 2, 3, 4. Yeah. So how to solve it? If we would like to obtain here 7, it is enough to write as an x and y 7 times more. Yeah. So the result of x will be minus 20,978 times 7. Yeah. And y will be 20,979 times 7. Yes, of course, if we put here these numbers, the result also will be 7 because we can take the 7 before the bracket. Is it clear? Yes, no, maybe? I'm sleeping?
I think so.
Oh, thank you. So the most stranger behavior of this, if we write it in the theorem form, is the fact that this is the only solution of such an equation. We can write this in the form of the theorem without a proof, because proof is not easy here, and we use it as a tool, in fact. But let us write like a fact theorem. An equation n times x plus n times y equals to k, m, x, n, y, k integers, has a solution if and only if. This notation is very famous in mathematics. We write it if f, like in such a way, and this means implication in both sides. So this is if and only if means from the left side we have right side, from the right side we have left side. So this is equality, logical equality. If and only if k is a multiplier of greatest common divisor of m and n. So, for instance, if we have such an equation, 4x plus 6y equals to 15, and x and y should be integers, we compute the greatest common divisor. Greatest common divisor on 4 and 6 is 2, as we can easily guess. And look, 15 is not a multiplier of 2. That means that this equation doesn't have any solutions in integer numbers. So this is quite a strong result that sometimes we can solve Diophantine equation, but if and only if on the right side we have greatest common divisor of or its multiplier. If we have as here 15 and greatest common divisor is 2, there is no solution. Okay, that's all I have prepared for today. Maybe only just for the last, we have also such a term as the smallest common multiply. Also sometimes we can use it, but the greatest common divisor is much more famous due to its applications. However, we can write such a thing. The smallest common multiply. So the in fact, this is the least common multiply, as I remember. The least common multiply, m and n. So this is minimal such a number k integer 1. The only positive, so in fact natural, that m divides k and n divides k. An example, or some properties, maybe. Properties. The least common multiply of m and n is m times n divided by greatest common divisor of m and n. So, for instance, an example 5. We can write such a thing that if we have, let it be here, we have m equals to 12 and n equals to 21. The greatest common divisor is 3, as here we have. Let us compute the least common multiplication. 12 times 21 divided by 3, so this is in fact 4 times 21. Yes, dividing it by 3, so we have 84. So this is such a the smallest such a number that both m and n, so 12 and 21, divides it without the rest. Any questions, remarks? Next week we will go to the factorization of numbers. Maybe we'll add some elements of the cryptography, and after it we'll go to the graph algorithm. But firstly, we'll follow these properties of factorization, of computing the factors of the numbers and using it. It is connected with very difficult part of the mathematics, connected with some hypotheses, Riemann hypothesis. So paradoxally, from very small, we can say, a part of the mathematics connected with natural and integers number, we can make a strong property about the numbers in general. But we'll see it in the next week. So thank you very much, and see you next Tuesday, 9:15. Thank you very much.
Thank you, goodbye.
Goodbye.
Thank you.